My name is Professor Gyom-Gi Beck, and I am Professor of Marine Technology in the Department of Mechanical Engineering at University College London. Today, I would like to share some perspectives on transformative technologies shaping the next century of the maritime sector. This lecture focuses on foundational and overarching concepts, rather than specific products or short-term trends. My aim is to step back and explore how emerging technologies, systems thinking, and new engineering philosophies may reshape maritime systems over the coming century. I hope this talk will offer a conceptual framework for thinking about the future of marine technology, one that emphasizes safety, sustainability, resilience, and human-centered design. Before we talk about technologies, we must understand why the next century of maritime development truly matters. Shipping is not just another industry. It is the backbone of global civilization. More than 90% of global trade by volume moves by sea, sustaining the world's food supply, energy security, and industrial production. What makes shipping fundamentally different from many other sectors is the longevity of its assets. Ships are not short-term products. They are long-life socio-technical systems designed to operate for several decades in continuous interaction with harsh environments, evolving regulations, digital technologies, and human operators. For over a century, maritime engineering has been guided by three enduring pillars: safety, sustainability, and cost-effectiveness. Today, these pillars are under unprecedented pressure. Nowhere is this more evident than in decarbonization, where the International Maritime Organization has set a clear ambition of achieving 100% zero-emission shipping by 2050. This means the next century of shipping cannot be shaped by incremental change. We are entering an era defined by artificial intelligence, digital twins, ultra-low latency communication via LEO satellites, and increasing autonomy. The ships we design today will operate in a far hotter, more uncertain, yet more connected world. If we step back and look at the last 150 years of maritime history, a very clear pattern appears. Shipping has evolved through a sequence of major technological leaps, from steam to diesel to automation and most recently, digitalization. These changes did not happen gradually. Roughly every 50 years, a disruptive technology emerged and reshaped the industry. Each leap fundamentally changed how ships were designed, operated, and regulated. Importantly, every transition reshaped three things at the same time: safety by introducing new risk profiles, labor by redefining crew roles and required skills, and economics by transforming efficiency, costs, and global trade. The key lesson is this: these transformations were never purely technical. They were systemic. New technologies demanded new regulations, new training, new organizational structures, and new ways of thinking about responsibility and risk. This is why history matters. It tells us that what we are facing today is not another upgrade. It is another system-level transformation. And the industry that understands this will lead the next century of maritime engineering. For more than a century, ships have been designed primarily for construction and certification, not for lifelong operation. We design, we build, we certify, and then we largely wait for failures. When something goes wrong, we inspect, repair, and return the ship to service. This inspect after failure paradigm served the industry well in the past, but it is no longer sufficient. Today's ships operate in a highly dynamic world, exposed to extreme weather, long-term aging, variable loading, and increasingly complex operational demands. Yet our rules and standards remain largely static, frozen at the design stage. At the same time, we still treat structures, machinery, human operators, and the environment as separate domains, even though real ships operate as tightly coupled systems. Modern accidents rarely originate from a single failure. They emerge from interactions across these boundaries. Conventional engineering has not failed. It has simply reached the limits of what it was designed to handle. For ships expected to operate safely and sustainably for over 50 years, a fundamentally new paradigm is required. Shipping today is not confronting a single dominant challenge. It is facing multiple crises converging simultaneously. Climate change is driving intense decarbonization pressure, while at the same time exposing ships to more frequent and more extreme weather events. Meanwhile, much of the global fleet is operating well beyond its original design life, with aging structures and machinery under increasing stress. Human factors have become equally critical. Crew shortages, fatigue, and rising system complexity mean that safety now depends as much on human system interaction as on physical hardware. Under extreme operating conditions, small errors or degradations can escalate rapidly into cascading failures. At the same time, modern ships are no longer purely mechanical assets. They are cyber-physical systems, dependent on data, connectivity, and software, and therefore exposed to cyber, data integrity, and system interaction risks. The key point is this: these challenges do not act independently. They interact, reinforce, and amplify one another. What we are facing is not a collection of isolated problems, but a systemic crisis, and systemic problems demand system-level solutions. For more than a century, we have treated ships as static products. We design them, build them, certify them, and then operate them until problems appear. This model was effective in a more predictable world, but it is no longer adequate. The ships of the next century will operate for 50 years or more in an environment defined by uncertainty, climate extremes, rapid technological disruption, progressive aging, and changing human roles. Under these conditions, the key challenge is no longer simply how to design a ship or how to operate a ship. The real question is how to care for a ship throughout its entire life. Structure, machinery, human operators, and the environment cannot be treated as independent domains. They are tightly coupled, evolving together as a single living system. Performance, safety, and sustainability emerge from their interactions, not from any one component in isolation. This marks a fundamental shift from ships as objects to ships as systems, and from engineering as construction to engineering as lifelong care. Everything that follows in this lecture is an attempt to answer this systems question. When we talk about decarbonization in shipping, the discussion is often reduced to a single question: which fuel should we choose? LNG, ammonia, hydrogen, methanol, or even nuclear are frequently presented as competing answers. But fuel switching alone will not deliver true decarbonization. True decarbonization requires fundamental changes in ship design philosophy. Enlarging ship size and extending design life from today's 25 years to 50 years or more are essential for CapEx optimization, allowing the initial investment, particularly for low carbon and nuclear technologies, to be amortized over much longer operational lifetimes. At the same time, longer design life enables OpEx optimization through reduced repair frequency, minimized downtime, and more efficient maintenance strategies. Every alternative fuel introduces system-level trade-offs: higher capital cost, lower energy density, new safety hazards, and increased operational complexity. If we focus only on emissions at the point of use, we often displace carbon and risk elsewhere, into construction emissions, fuel production, port infrastructure, or shortened asset life. These challenges become even more critical for SMR-powered ships, where decarbonization must be balanced against radioactive leak prevention, robust containment, and continuous safety assurance. Likewise, fully autonomous Level 4 ships operating without crew on board cannot rely on traditional human-centered inspection and intervention. For both cases, real-time, life cycle, intelligent healthcare, and operational management is no longer optional. It is indispensable. This is why decarbonization must be treated as a life cycle systems problem, not a component-level choice. CAPEX, OPEX, safety margins, operational reliability, and total life cycle emissions must be optimized together, continuously and adaptively. The ships of the next century will only be genuinely low carbon if they are designed as integrated energy and information systems, supported by AI and digital twin-driven real-time monitoring and decision-making across their entire lifespan. In this sense, decarbonization is not merely a fuel problem. It is a systems engineering and operational philosophy problem. Safety in shipping has always been tested by extreme events, collisions, groundings, flooding, and loss of stability. What has changed is the frequency, intensity, and unpredictability of these events. Climate change is exposing ships to harsher seas, stronger storms, and more complex operational pressures than those assumed at the design stage. Crucially, modern maritime accidents are rarely caused by a single failure. A collision may trigger flooding, followed by power loss, degraded human performance, impaired decision-making, and ultimately cascading system collapse. Yet traditional safety frameworks still tend to address structures, machinery, and human factors in isolation, struggling to capture these coupled failure mechanisms. The stakes rise even higher with energy-dense propulsion systems and nuclear-powered ships. In these cases, safety margins are narrower and the consequences of failure far more severe. Preventing failure alone is no longer sufficient. What is required is a fundamental shift in safety philosophy, from designing ships to avoid failure to designing ships to survive failure. This means inherent crashworthiness, real-time situational awareness, and system-level resilience that allows ships to absorb damage, adapt to evolving conditions, and recover safely under extreme and unpredictable scenarios. Most ships are originally designed for a nominal service life of around 25 years. Yet in practice, many continue operating for 40, 50 years, or even longer. This widening gap between design intent and operational reality has become one of the most serious and systemic challenges facing the maritime sector. As ships age, they inevitably suffer from corrosion, fatigue cracking, machinery degradation, and growing uncertainty in structural capacity. Yet despite this increasing complexity, our primary safety mechanism remains largely unchanged: periodic inspection and survey. These inspections are intermittent, often subjective, and provide only a snapshot of a continuously evolving system. Crucially, damage does not wait for surveys. Corrosion progresses, fatigue accumulates, and machinery degrades continuously, while many critical failures initiate and develop between inspection intervals when early warning signs remain undetected. As global fleets continue to age, the fundamental question is no longer whether ships can operate longer. The real question is whether we can know their true condition in real time. Without continuous health awareness, life extension becomes a gamble rather than a rigorous engineering decision. As ships become more complex and more digital, the human role on board is not diminishing. It is intensifying. Crew numbers are decreasing, yet cognitive demands are rising sharply. Seafarers are expected to monitor multiple interconnected systems, interpret large volumes of data, and make high-stakes decisions, often under conditions of fatigue, isolation, and time pressure. Many maritime accidents today are not caused by hardware failure alone, but by breakdowns in human system interaction, misunderstood alarms, delayed or inappropriate responses, and cognitive overload at critical moments. These failures emerge not from incompetence, but from systems that were never designed around human limitations. This exposes a fundamental misconception in conventional engineering. Humans are still treated as external operators of ships, rather than as integral components of the system itself. In reality, safety is an emergent property arising from the interaction between humans, machines, software, and the operating environment. If we want safer ships in the next century, we must design systems that support human performance rather than overwhelm it. Human-centered engineering is therefore not optional. It is a core safety requirement. The maritime sector is undergoing rapid digitalization. Modern ships are filled with sensors, dashboards, and data streams measuring almost everything: structural loads, motions, machinery performance, and environmental conditions. Yet paradoxically, many operators report the same experience: more data, but less understanding. The core problem is that data alone does not create intelligence. Without physical meaning, context, and integration, sensor data quickly becomes noise rather than insight. This is why many so-called digital twins remain disconnected from reality. Built as static models, updated infrequently, and ultimately not trusted in operational decision-making. When digitalization adds complexity without improving safety or reliability, it becomes an illusion of progress rather than real advancement. The real opportunity lies not in collecting more data, but in transforming data into actionable knowledge. This requires tightly coupling real-time sensing with physics-based digital twins, engineering models, and domain expertise. Only then can digital systems explain why something is happening, not just what is being measured. Only under these conditions does digitalization become a tool for safety, resilience, and informed decision-making, rather than a source of confusion. Taken together, the challenges we have discussed point to a deeper and more fundamental issue: the limitations of our current engineering philosophy. Despite the growing complexity and extended lifetimes of modern ships, we still rely heavily on inspection after damage, reactive maintenance, and component-by-component thinking. This approach is increasingly misaligned with how ships actually operate, as long-life, tightly coupled socio-technical systems. What is required is a paradigm shift from inspection to healthcare. Just as in modern medicine, the objective is no longer to respond to failure after it occurs, but to maintain health proactively through continuous monitoring, diagnosis, and early intervention. This shift also demands a move from reactive to predictive engineering, where emerging risks are identified and managed before they escalate into incidents or accidents. It requires abandoning isolated component thinking in favor of understanding ships as integrated ecosystems, where physical structures, machinery, digital systems, human operators, and the environment continuously interact. Crucially, this new philosophy does not replace traditional engineering. It extends and elevates it. It builds upon established design, analysis, and safety principles, while enabling them to operate effectively in a world defined by uncertainty, aging, and digital complexity. This is the foundation of the transformative framework I will introduce next: digital healthcare engineering. The transformative technologies shaping the next century of maritime engineering do not act in isolation. Sensors, artificial intelligence, digital twins, secure communication, high-performance computing, and autonomy are often discussed as separate innovations, but their true power emerges at their intersections. Sensors without intelligence produce data, but no understanding. AI without physics lacks credibility and trust. Digital twins without real-time data become static representations. Secure communication without analytics adds infrastructure but little value. Autonomy without human-centered design introduces risk rather than safety. Transformation occurs only when these technologies converge into a single coherent system, where real-time sensing continuously updates physics-based digital twins, AI interprets system health and emerging risk, secure communication ensures trust and integrity, and high-performance computing enables continuous prediction and foresight. This convergence represents a fundamental shift from digitizing individual components to creating intelligent cyber-physical maritime systems. The next century of maritime engineering will not be defined by individual technologies, but by how effectively we integrate them into living, adaptive, and trustworthy systems. Traditionally, digital models in ship design have been static artifacts. They are created during the design stage, used for approval and certification, and then largely forgotten once the ship enters service. In this paradigm, the digital model's life ends where the ship's real life begins. In contrast, the digital twins of the next century must become living companions, evolving continuously throughout a ship's entire operational life. A living digital twin is continuously updated using real-time operational and environmental data. It evolves as the ship ages, as damage accumulates, and as operating conditions change. It reflects not only the ship as designed, but the ship as it actually exists and behaves. This is neither a purely data-driven model nor a purely physics-based one. It is a fusion of both. Physics-based models provide causality, interpretability, and safety margins. Data-driven methods provide adaptability, learning, and sensitivity to real operational behavior. Together, they enable reliable prediction of structural response, system performance, degradation, and remaining useful life. In this new paradigm, the digital twin is no longer just a design or verification tool. It becomes a persistent engineering partner, supporting operational decisions, anticipating emerging risks, guiding maintenance strategies, and enabling ships to be safely and confidently operated far beyond their original design assumptions. Artificial intelligence is already widely applied in maritime systems for pattern recognition, detecting anomalies, classifying signals, and optimizing operations. However, for safety-critical systems such as ships, this capability alone is insufficient. The next century requires a decisive shift from AI as a statistical tool to AI as engineering intelligence. Engineering intelligence means that AI must understand why something is happening, not merely that it is happening. This is where physics-informed AI becomes essential. By embedding physical laws, structural mechanics, thermodynamics, and system constraints into learning models, AI gains robustness, consistency, and engineering credibility. With this foundation, AI moves beyond simple detection. It enables diagnostics, prognostics, and decision support, identifying root causes, predicting damage evolution and remaining useful life, and recommending safe and effective actions under uncertainty. Crucially, explainability is non-negotiable. Engineers, operators, and regulators must be able to understand, validate, and justify AI-driven decisions. In maritime engineering, an AI system that cannot explain its reasoning is not intelligent. It is unsafe. In the next century, data transmission will become as fundamental to ships as steel, engines, and fuel. Real-time monitoring, living digital twins, and AI-driven decision-making all depend on reliable, continuous, and secure data flows between ship and shore. Satellite communication, particularly through global and low-latency networks, enables ships to transmit operational, structural, and environmental data in real time anywhere in the world. However, connectivity alone is not sufficient. Without data integrity, provenance, and trust, digital information cannot be used confidently for safety-critical engineering decisions. This is where blockchain-secured data transmission becomes essential. By ensuring that data is tamper-proof, traceable, time-stamped, and verifiable, blockchain establishes a shared foundation of trust across all stakeholders: ship operators, designers, classification societies, regulators, and insurers. Secure data infrastructure fundamentally changes the role of data. It transforms data from a private operational asset into a trusted engineering resource capable of supporting certification, life cycle management, and regulatory decision-making. In the future, trust in maritime systems will be built not only on physical strength and redundancy, but also on the integrity, transparency, and reliability of the data that represents their health. Energy sovereign ships are vessels capable of producing, managing, and sustaining their own energy safely and reliably over their entire operational life, with minimal dependence on external fuel supply chains or port-based energy infrastructure. Energy sovereignty is therefore not only about low emissions, but about long-term autonomy, resilience, and life cycle integrity. Viewed through this lens, decarbonizing shipping at a century scale raises a deeper challenge than fuel substitution. Future ships must be designed as self-contained energy systems, able to support propulsion, onboard systems, and safety functions continuously over 50 to 100 years of operation. Technologies such as small modular reactors and advanced alternative fuels offer unprecedented energy density, endurance, and operational stability. At the same time, they fundamentally change the nature of ship design. Vessels powered by energy-dense systems are no longer short-life transport assets. They become long-life maritime infrastructure. This shift transforms the role of structural design and safety philosophy. Safety can no longer rely primarily on operational procedures or human intervention. It must be physically embedded in the ship itself through crashworthy structures, robust shielding, system segregation, and fail-safe layouts that remain effective under extreme and accidental conditions. Energy sovereign ships therefore demand a new regulatory paradigm. Prescriptive rules alone are insufficient for systems expected to operate across decades of uncertainty. What is required is life cycle, performance-based safety assurance, supported by continuous monitoring and verification. In the next century, energy will define not only how ships are powered, but how they are designed, operated, and governed. Autonomy in shipping is often misunderstood as the removal of humans from ships. In reality, the next century will be defined not by human absence, but by human repositioning. Autonomy exists across a spectrum, from decision support and conditional automation to fully autonomous operation. And at every level, the human role is transformed rather than eliminated. In advanced autonomous systems, humans act primarily as supervisors and guardians rather than continuous operators. They intervene in abnormal or unexpected situations, validate safety-critical decisions, and apply ethical and contextual judgment where algorithms alone are insufficient. This human-in-the-loop principle is essential for safety, accountability, and trust in maritime operations. At the same time, autonomy introduces new and subtle risks. Over-reliance on automation, erosion of situational awareness, skill degradation, and ambiguity in responsibility when failures occur. These risks cannot be mitigated by technology alone. For this reason, ethical, operational, and safety boundaries must be embedded into autonomous systems from the outset, not added as afterthoughts. The objective is not autonomous ships versus human-operated ships, but resilient socio-technical systems in which humans and machines work together, each performing the roles they are best suited for. in the next century of maritime engineering, autonomy will succeed only where human judgment remains an integral part of the system. At this point, I would like to introduce the unifying framework behind everything we have discussed so far: Digital Healthcare Engineering, or DHE. DHE represents a fundamental shift in engineering philosophy. Within this framework, ships are no longer viewed as static assets or disposable products. Instead, they are treated as patients. Correspondingly, engineering is no longer confined to design, inspection, and repair. It becomes healthcare. Healthcare implies continuous care across the entire life cycle. It is based on real-time monitoring, early diagnosis, predictive assessment, and timely intervention, long before failure occurs. Just as in human healthcare, the objective is not to wait for collapse, but to preserve health, functionality, and resilience over time. Digital healthcare engineering integrates real-time sensing, living digital twins, secure data transmission, and AI-driven intelligence into a single, coherent lifecycle framework. It enables ships to be designed, operated, monitored, and cared for as living systems, adapting continuously to aging, uncertainty, and changing operational demands. In the next slides, I will show how DHE transforms this philosophy into a practical and implementable engineering reality, reshaping safety, sustainability, and resilience for the next century of maritime systems. Healthcare for engineering structures and machinery systems is closely analogous to healthcare for human beings. When we use the term healthcare in an engineering context, we are not speaking metaphorically. Rather, we are redefining the scope of engineering responsibility. In this sense, healthcare means the continuous preservation of system health, rather than episodic inspection and repair after damage has already occurred. For ships, this concept of healthcare encompasses four inseparable dimensions. First, structural integrity. The continuous monitoring of stresses, fatigue accumulation, corrosion, damage initiation, and damage evolution. Second, machinery condition. Understanding performance degradation, efficiency loss, wear, and the development of faults over time. Third, environmental exposure. Capturing the real operational loads imposed by waves, wind, temperature, and increasingly severe climate extremes. Fourth, human well-being, recognizing that fatigue, cognitive load, and working conditions directly influence safety, decision-making, and overall system performance. These dimensions cannot be managed in isolation. Harsh environmental conditions accelerate structural degradation. Degraded machinery increases human workload, and human fatigue in turn raises the likelihood of operational error and accidents. True engineering healthcare is therefore preventive and holistic. It shifts the role of engineering from fixing failures to maintaining health, continuously, intelligently, and across the entire socio-technical system. Digital healthcare engineering is not a single technology. It is a structured life cycle framework built upon 5 tightly integrated modules, each essential to the integrity of the whole system. The first module is real-time multimodal sensing. This provides continuous data streams from structures, machinery, the operating environment, and human operators, forming the nervous system of the ship. The second module is secure data transmission. This ensures that sensed information is reliably, continuously, and securely transferred between ship and shore, with data integrity, traceability, and trust preserved. The third module is digital twin simulation. Here, physics-based models are continuously updated with real-time data to represent the true evolving state of the ship, rather than an idealized design condition. The fourth module is AI-enhanced diagnostics. AI interprets digital twin outputs to detect anomalies, identify root causes, and assess emerging and future risks under uncertainty. The fifth module is predictive health management. This module transforms diagnosis into actionable decisions, optimizing maintenance strategies, operational planning, and long-term lifecycle management. These 5 modules do not operate independently. They function as a single, coherent healthcare system. Remove any one module, and the effectiveness of the entire framework collapses. Together, they enable continuous, intelligent life cycle care of ships as living engineering systems. One of the most powerful features of digital healthcare engineering is that it spans the entire life cycle of a ship, from the earliest concept design to final decommissioning. DHE is not an add-on applied after delivery, it is embedded from the very beginning. At the concept and preliminary design stage, digital twins are used to explore safety margins, energy system choices, structural robustness, and long-term performance under uncertainty. Design decisions are informed not only by compliance, but by predicted life cycle health. During construction, real-time sensor data and digital models are used to ensure that the ship being built faithfully matches the ship that was designed, reducing hidden defects and ensuring traceability from yard to operation. Once the ship enters service, the digital twin becomes a living companion, continuously updated to reflect real operational loads, environmental exposure, degradation, and usage patterns. This enables informed, evidence-based decisions on maintenance, operation, and risk management. As the ship ages, DHE supports safe and economical life extension by quantifying remaining useful life and evolving safety margins, rather than relying on conservative assumptions or calendar-based rules. Finally, at decommissioning, accurate digital records support safe dismantling, waste management, and environmental responsibility, closing the life cycle loop. In this way, DHE transforms ship engineering into a true cradle-to-grave discipline, grounded in continuous knowledge and healthcare, rather than periodic inspection and fragmented snapshots. Let me now illustrate how digital healthcare engineering operates in practice, beginning with structural healthcare. Traditionally, structural integrity has been assessed through periodic inspections, simplified calculations, and conservative design assumptions. DHE replaces this episodic approach with continuous quantitative health assessment. In a DHE framework, real-time sensors continuously measure structural stresses, motions, fatigue accumulation, and corrosion progression under actual operating and environmental conditions. These data streams feed directly into nonlinear finite element digital twins capable of capturing realistic structural behavior, including plasticity, buckling, progressive damage, and collapse mechanisms. By tightly coupling real-time data with physics-based simulation, DHE enables continuous estimation of remaining useful life, rather than relying on fixed design life assumptions. This allows engineers to clearly distinguish between benign aging and emerging structural risk. Structural healthcare, therefore, is not about identifying failure after it occurs. It is about understanding how close a structure is to its true safety limits and intervening early while safe, practical, and cost-effective options still exist. Digital healthcare engineering is equally transformative for machinery and energy systems, where unplanned failures are costly, disruptive, and potentially hazardous. Rather than relying on fixed calendar-based maintenance intervals, DHE enables condition-based and predictive maintenance driven by real operational data. Within a DHE framework, real-time sensors continuously monitor key parameters: vibration, temperature, pressure, efficiency, load, and wear across engines, generators, propulsion systems, energy storage, and power management systems. These data streams feed digital twins of machinery and energy systems, enabling early detection of deviations from healthy operating behavior. AI-enhanced diagnostics then move beyond simple threshold alarms. They enable fault diagnosis and prognosis, identifying not only that something is abnormal, but what is likely to fail, why it is failing, and when intervention is required. At the same time, digital twins support energy system optimization, balancing performance, fuel or power consumption, emissions, thermal limits, and component health under real operating conditions. Machinery and energy healthcare therefore transforms operations, from reactive repair and emergency response to intelligent planning and proactive intervention. The result is reduced downtime, improved safety, higher efficiency, and extended life of critical energy systems. Digital healthcare engineering does not stop at steel and machinery. It explicitly recognizes human well-being as a core element of system safety. In complex maritime operations, the health of the ship and the health of the crew are inseparable. Within a DHE framework, fatigue is monitored proactively, using a combination of work-rest patterns, operational schedules, wearable or onboard sensors, environmental conditions, and voyage context. This enables the early identification of excessive fatigue long before it manifests as human error or accidents. Beyond physical fatigue, DHE also addresses cognitive load. It recognizes when operators are overloaded by alarms, information flows, or decision pressure, particularly during abnormal operations, emergencies, or high-consequence situations. By integrating human state data with structural and machinery data, DHE supports safe manning strategies and intelligent operational planning. Workload, automation level, and human capability are continuously aligned rather than assumed to be constant. Crucially, this must be achieved with strict ethical safeguards. Transparency, data minimization, privacy protection, and informed trust are essential. Human data must be used to support people, not to monitor or penalize them. In the next century, caring for ships means caring for people, not as external operators, but as integral components of a living maritime system. When all the elements we have discussed come together, ships of the next century can no longer be viewed as static machines. They must be understood as living cyber-physical systems, continuously aware of their own condition, their operating environment, and their operational context. A living ship is self-aware. It continuously senses structural stresses, material degradation, machinery health, energy flows, environmental loads, and human performance. Through the integration of real-time sensing, digital twins, and AI, it is also self-diagnosing, interpreting what this information means for safety, reliability, and long-term integrity. A living ship is also continuously learning. As it operates, it refines its digital models, improves predictive accuracy, and adapts to new conditions and behaviors, rather than relying on assumptions frozen at the moment of delivery. Most importantly, these ships are designed for longevity. They are conceived to operate safely and efficiently for decades, with health awareness embedded from the outset, enabling informed life extension rather than premature obsolescence. This does not imply that ships become autonomous organisms. Rather, it signals a fundamental evolution in engineering, from building inert objects to sustaining living systems where awareness, learning, and care are central design objectives. In this paradigm, safety and sustainability are no longer enforced intermittently. They are continuously maintained as intrinsic properties of the system itself. Traditionally, ship design has focused on preventing failure. However, in a world characterized by uncertainty, extreme events, and long service lives, absolute failure-free operation is neither realistic nor achievable. The ships of the next century must therefore be designed to be failure-tolerant, capable of surviving, adapting, and recovering when things go wrong. Resilience can be understood through three essential capabilities. First, anticipation, recognizing emerging risks before they escalate, enabled by real-time monitoring, prediction, and situational awareness. Second, absorption, maintaining critical functions during extreme or abnormal conditions through robust structures, redundancy, and adaptive operation. Third, recovery, restoring functionality safely, efficiently, and decisively after damage or disruption. Digital healthcare engineering provides the enabling infrastructure for all three capabilities. By integrating continuous sensing, living digital twins, AI-driven intelligence, and secure data transmission, DHE allows ships to understand their own condition, respond intelligently under stress, and support informed decision-making during and after extreme events. Resilience thus becomes a deliberate design objective, not an accidental byproduct of conservative design. In the next century, maritime safety will be judged not only by how effectively ships avoid failure, but by how robustly they endure, adapt, and recover from it. The transformation we are discussing does not stop at technology. It fundamentally reshapes the relationship between industry and regulation. Traditional maritime regulation has relied heavily on prescriptive rules, fixed requirements derived from assumed scenarios at the design stage. While effective in the past, these rules struggle to keep pace with long-life ships operating under uncertainty, aging, and rapidly evolving technologies. In the next century, regulation must progressively shift toward performance-based frameworks. Instead of asking whether a ship complies with static rules, the central question becomes whether it can continuously demonstrate safety, reliability, and resilience under real operating conditions. This shift also transforms the role of regulators. Regulators evolve from periodic auditors into data partners, engaging with trusted, real-time information generated by ships, living digital twins, and digital healthcare engineering systems. Oversight becomes evidence-based, continuous, and adaptive. As digital twins and AI increasingly inform safety-critical decisions, certification itself must evolve. Certification will no longer apply only to steel and hardware, but also to models, algorithms, data quality, and data integrity, ensuring that digital systems used in decision-making are transparent, validated, and trustworthy. In this new regulatory landscape, trust is built through transparency, continuous evidence, and shared responsibility between industry and authorities. Regulation moves beyond enforcing minimum compliance toward enabling sustained life cycle safety and resilience across the entire operational life of a ship. The transformation of maritime systems demands an equally profound transformation in engineering education. The next generation of engineers will no longer be trained merely to design components or analyze isolated failures. They must be prepared to act as system doctors. A system doctor understands how structures, machinery, software, humans, and the environment interact across the entire life cycle of a ship. This requires interdisciplinary thinking, integrating mechanics, materials, data science, artificial intelligence, human factors, and systems engineering into a coherent whole. Technical excellence alone is no longer sufficient. Engineers must also be ethically literate, capable of judging how data is collected and used, how decisions are automated, and how responsibility is shared when humans and machines collaborate. In this context, AI literacy becomes as fundamental as structural mechanics. Equally important is the recognition that humans are integral components of engineered systems. Understanding fatigue, cognition, workload, and human-machine interaction is not optional. It is central to safety, resilience, and performance. Educating the next generation therefore means cultivating engineers who can care for complex systems with technical competence, ethical responsibility, and humanity, ensuring that future maritime systems are not only smarter, but safer and more humane. Let me close with a vision for the next century of marine technology. The future will not be defined by any single technology. It will be defined by a fundamental change in how we think about ships and in our responsibility toward them. The ships of the next century must be safer, resilient to extremes, aware of their own condition, and capable of preventing failure rather than merely reacting to it. They must be cleaner, not only in terms of propulsion and fuel, but across their entire life cycle, from design and construction to operation and decommissioning. They must be smarter, able to learn, adapt, and support informed, timely decisions through real-time intelligence. But above all, they must be more humane. They must be designed to protect human well-being, to support the ethical use of data and automation, and to recognize that people remain central to safety even in an era of autonomy and AI. This is the ultimate shift I have proposed today, from ships that are merely operated to ships that are genuinely cared for throughout their lives. If we embrace this shift, marine technology will not simply keep pace with the next century, it will help shape it responsibly, sustainably, and humanely.